Hey everybody, welcome back to another round of astronomy. And yeah, let's get going. Question for you. A rich uncle dies and leaves his inheritance to his nieces and nephews, one of which is you. I'm sorry for your loss. However, you do get an inheritance, so there's a bright silver lining here. The question I have for you, how many cousins do you wish you had? Yeah. So, I mean, this just gets you thinking. And the issue is that most people would say, oh man, I hope that I have 0 cousins. And why is that? The less cousins you have, the more money you get, right? If you take your uncle's wealth and divide it by the number of cousins plus 1, don't forget that plus 1, that's you. Okay, your share is equal to this, right? You take your uncle's wealth, you divide by the total number of nieces and nephews, and that gives you your share. Well, if in order to get the most amount of money, that means that you want this number that I'm underlining to be as small as possible, namely 0. If this number is 0, you get all the money. Okay, so I'll call this the rich uncle problem, right? The more cousins you have, the less money you get. Okay, so here's the next question for you. We're going to go, this is getting into our discussion about luminosity versus brightness. How bright an object appears to be as versus how bright an object is. Okay? So the next question I have for you. Say that you want to surround a star with solar panels. Okay, you want to collect all of the light coming from that star. In order to use the fewest number of solar panels, do you want to surround the star far away from the star, or do you want to get as close as possible to the star in order to encompass it with solar panels? Yeah, and I'll give you a picture here, of course. Yeah. Good. In order to use the fewest number of solar panels, you want to be as close to the star as possible, right? In order to do, why is that? Because the closer you are to the star, the smaller area you need to cover. And if you have a smaller area, that means that you use less solar panels. Here comes the next question. Corollary. For which situation does a single solar panel collect more light? You got it? Yeah, good. Well, and it's the rich uncle problem. You have a fixed amount of light given off by the star. Okay? If you have a fixed amount of light and less solar panels, that means that each solar panel collects more light. This is the rich uncle problem, except instead of money, I'm talking about starlight. And instead of cousins, I'm talking about solar panels. Next question. And now we're going to start getting a little bit of quantification in here. In order to do this next question, I would like to know how much more light. Okay? So we're going to start using numbers. The thing that I need to provide for you is the equation that gives you the surface area of a sphere. So let me give you that equation. That equation, the area of a sphere, is given by 4 pi times the radius of the sphere squared. So you could do this for a basketball or a softball, or the Earth, for example. As long as you know the radius, you can determine the area of the sphere. Okay? Well, let's get some practice. Question for you. So if I use the same size solar panels, but place them twice as far away from the star, okay? How many more solar panels do I need? So now I'm asking you to quantify. So I've got a picture here. Of course, we'll say that this is, I choose some distance and here I surround it. Over here, I choose a distance that's twice as large and I surround the star. Go ahead, figure out for me how many more solar panels I need. You got it? Yeah, good, good, good. And the whole idea, okay, the number of solar panels that I need is proportional to the area that I have to cover. So if I double the area, that means I need twice as many solar panels. Or if I quintuple the area, I need, what was quintuple? 5 times as many solar panels. So what we first need to figure out is the ratio of the areas. Well, let's do that. I haven't given you any numbers, so we'll just have to leave it in terms of variables. So the area of the small sphere is just 4 pi, and I'll label it as the radius of the small sphere squared. Well, how about the big sphere? I would do the same thing, except notice I said that the big sphere has twice the radius, right? I place it twice as far away. That means that the big sphere has twice the radius. So instead of putting r squared, I've put 2r small squared. And now we have to be careful. Don't forget that I have my parentheses. I have to square everything inside the parentheses. That includes the variable r small and also the 2. Square everything. So I go ahead and plug in my numbers, and I get that I have the area of the small sphere. That's the thing I've underlined in yellow. And notice that I have that 4 out in front. Good so far? Okay, next question for you, and quantitative. Okay? So thinking about a solar panel on the surface of the small sphere and a solar panel on the surface of the large sphere, how much more light does the solar panel on the small sphere collect as compared to that on the large sphere? Right now we're quantitative with the rich uncle problem. On the large sphere, I need 4 times as many solar panels, which means each solar panel on the large sphere must collect 1/4 of the light that the solar panel does on the small sphere, right? Same amount of light. I have 4 times as many solar panels. Thus, each solar panel must collect 1/4 the amount of light. Okay, so let's pull this all together. So quantitative, okay? Term for you, I'll say luminosity. Okay? The luminosity of a star is the total amount of light that the star emits. Okay? The luminosity of a star does not change. It depends on the star itself, not how far away you are viewing it. But you know that something does change, and that comes back to the figure that we were looking at the beginning of the lecture. What changes is not the total amount of light emitted by the star, but rather the total amount of light that your solar panel receives. You know that if you move further away from the star, the surface area of a sphere surrounding the star increases, meaning that every solar panel on the surface of that fictitious sphere collects less light. And because it collects less light, the brightness of the star will appear dimmer. So the apparent brightness is how much light you collect when you observe from a distance away. And that depends, of course, on the distance. Synonyms for this would be the intensity or the flux. Okay? And I've given you units. It's called the watts per square meter. Okay? Watts are a unit of power. It's the same unit that's used on your light bulbs. It says how much energy per second. Okay? Now there's a quantitative relationship, and you can probably already give it to me now. If I take the total luminosity of a star and I divide it by the surface area of a sphere surrounding the star, that will tell me how much light each solar panel on the surface of that sphere collects. In other words, the apparent brightness, lowercase b, is equal to the luminosity divided by the surface area of a sphere. Okay? So I'll subscript this, I'll say apparent brightness, and this is distance from source. So as you get further away from your light source, the apparent brightness should go down. Okay. As you get closer, it goes up. Cool? Okay. So let me give you something to chew on here. Okay. When we send spacecrafts out into orbit, okay, some spacecrafts use solar power. The ISS would be a good example, but many spacecraft, say the ones that we send to Mercury, the Sun, Venus, even Mars, use solar panels. Why don't we use solar panels when we send a spacecraft to Saturn? Why don't we power our spacecrafts with solar panels when they fly past Pluto? Yeah, good. In fact, you probably already got the idea, right? The intensity, the apparent brightness of the sun is so dim when we're that far away that it's technologically not possible for us. Not technologically possible. It is impractical for us to have a spacecraft with such a large panel of solar arrays. Let me give you the example. For example, a satellite orbiting the Earth needs 2 square meter solar panel in order to operate. Okay, so 2 solar panels, I'm just estimating, 2 solar panels, squared meters, in order to operate. How large does a solar panel need to be if we had this satellite out at Jupiter instead? Go ahead, take a minute, see if you can come up with it. Oh, and incidentally, Jupiter is at 5 astronomical units. You got it? Yeah, good. So let's just go ahead and calculate it out for a second. The apparent brightness, as seen from Earth, would be something like the luminosity of our star divided by 4 pi, and then our distance from the sun. I'll leave it like this: the distance to the Earth squared. Okay, so this would be the Earth-Sun distance, 1 astronomical unit. Well, what's the brightness, the apparent brightness, when seen from Jupiter? Well, that would be the luminosity of our sun, 4 pi, and now, yeah, it would be 5 AU. So 5 times the distance of the Earth to the sun. Squared. Okay? So in other words, now we would need, the apparent brightness would be a factor 25. Right? So if you're out beyond Jupiter, you're going to need a solar panel that's like the size of a couple football fields in order to collect enough light in order to operate. That is, from a practical standpoint, not possible. Even if you fold it up, unfolding it, and it's not going to work. You have to find a different way of doing the energy. So for example, if you do a colony on Mars, you're going to need a lot more solar panels in order to produce the electricity than you would need comparably here on Earth. It's just the fact that the sun appears to be dimmer. Okay? Now, the thing I'll highlight here, okay, is that if you can get an idea about the luminosity of an object, and you can observe how bright it appears to be, then you can get an estimation for how far away the object is. I'll say that again. If you can get an idea about the luminosity of an object, how bright it truly is, and you can go out and observe how bright it appears to be, you can find out how far away the object is. And that will be our first foray into measuring distances beyond our solar system. Okay? So hopefully you'll stay tuned for that. We're going to get through a couple more ideas before we get into that, but that's where we'll go in the future. So I think that's enough for this lecture video. I thank you for your attention. Keep up the good work. I'll see you next time.